Okay, hi again, everyone. Professor Sebastian back with our our Calculus 3 class notes. And we're now moving on to section 14.3. I skipped section 14.2 on purpose. That's a discussion of a more rigorous understanding of limits when I get into functions of more than one variable, and it's not necessary for the understanding of what I want you to get out of Calc 3. So we're going to skip that section and just move on to the section on partial derivatives. And the limits that we talk about are similar to limits that we've been doing before in Calc 1 and Calc 2. So it's not worrisome to skip section 14.2. Okay, so consider we got to talk about what is a partial derivative. So I kind of will always draw this thing. I actually talked about it in class the other day a little bit, but this is just a generalized surface, z equals f of xy. Okay, so, and I kind of want you to visualize it. I mean, I guess it kind of looks like a whale or a fish or something like that. I kind of refer to him as Herbie after a while because I think I told you the story when I grew up in Northern California in the Sacramento Valley. We have a Sacramento River, and when I was a kid, a whale swam like 100 miles up the river and kind of got stranded in the river, and it was like a big deal in the news and everything. So I always remember Herbie the whale. We named him Herbie the whale. But anyways, not that important. This is just a generalized surface, okay? So you can kind of see the depth I put in it with these contours over here, okay? Okay, so just look at this guy. What I'm saying is we have down here in the xy plane, we have a point x naught, y naught, and you can think of that up here on the surface of the generalized surface, our whale-looking creature here. That's the function value at x naught, y naught. In other words, it's the height. It's what exactly that point lies on the surface. Z equals f of xy. So for the point x naught, y naught down in the domain in the xy plane, that is your z value right up here for the function at that value. Okay. Now, the partial derivative. I'll come back to this. You got to really draw this after you understand what the partial derivative is. So the partial derivative of f of xy with respect to x. So now when I talk about taking the derivative of a function of more than one variable, its domain consists of x's and y's, not just x, right? So what we need to do is think about what the partial derivative is, but in different directions. So in this case, with respect to x, at the point x naught, y naught, is defined as the following. So it looks very similar, except that notice my x plus h is only with the x. The y naught stays the same. So the limit as h approaches 0 of f of x naught plus h y naught minus f of x naught, y naught, all divided by h. So we're not going to actually be evaluating these limits like when you first learned derivatives in Calc 1, but I just want you to understand that's what it is. Okay, now what exactly is it physically? So in the direction of the x-axis, it's the slope of the tangent line if the tangent line was lying parallel to the x-axis. Okay, so that's what the partial derivative of f with respect to x is. Now notice the notation I use. I don't write df dx like we would before. We use the little Greek d, which is del. So I'll often say del f by del x. Okay, del f by del x means the partial derivative of f with respect to x. If I actually evaluate it, so this line with the point to the right of it says evaluated at x naught, y naught. So it's the partial derivative of f with respect to x, or del f del x, or del f by del x, evaluated at the point x naught, y naught. That gives me some value, some number, some real number. That is the slope in the tangent line for the line that is parallel to the x-axis. So it's the instantaneous rate of change of the surface at the point x naught, y naught in a direction parallel to the x-axis. In other words, perpendicular to the y-axis at y equals y naught. So again, that above picture, you can take a look at it. Now other notations, instead of putting a line and then x naught, y naught, you can just have the partial with respect to x, or del by del x of f of x naught, y naught. Some people really don't like to use this notation, so they'll go to a shorthand notation where they'll say f sub x. Now that sub x means the partial derivative of f. And then if you put at x naught, y naught, it means you take the partial derivative of f and then evaluate it at x naught, y naught. Or some people will write del z by del x, right, like that. So because z equals f. And this is just another way to write it. So if we simply want this partial derivative not evaluated at a specific point, but written as a function, then we just write it as f sub x, del f by del x, z sub x, or del z by dx. Okay, and on the next page, it's all similar, okay? Except that if I take the partial derivative of f with respect to y, del f by del y, that means it's in a direction that is parallel to the y-axis now instead of the x-axis. Okay, probably a different slope. Still evaluated at x naught, y naught, same point down in the domain. But now notice where the limit is. It's at y naught plus h. So f of x naught, y naught plus h minus f of x naught, y naught. So you're adding h to the y naught only, not the x naught. So this gives the instantaneous rate of change of the surface in a direction parallel to the y-axis at that point. In other words, perpendicular to the x-axis. So the notations are all similar to what we talked about on the previous page, except we have y's instead of x's.